roads in several inches of ice. So I'm going to talk about small stars, M-dwarfs, and exoplanets. And we're going to start by talking about stars and then move into exoplanets at the end. So to set this stage, this is the view of the night sky, as long as your lights aren't too bright, that I actually have here in Vermont. So Dartmouth College is right on the border with Vermont, and I live in rural Vermont. And when I'm taking out the trash at night, as long as it's actually clear, you can actually see the Milky Way just from right outside the house, which is awesome. So the most common type of star in the galaxy is an M-dwarf star. And as Tony already mentioned, that's going to be one of the focuses of my talk today. So M-dwarfs comprise about 70% of all of the stars in the Milky Way galaxy. And they're also the smallest and least bright type of star. And one of the consequences of that is that despite the fact that I can see the Milky Way, like the line of the Milky Way galaxy, I still can't see any M-dwarf stars. So even though they are so numerous, they're very intrinsically faint. And so you can't see a single one of them by eye. But if we can take some creative license, I'm going to crank up the red sensitivity of this planetarium software that I used to create this video. And each of these red dots now represents an M-dwarf star. So if you could do this with your eyes, you would actually see that M-dwarfs really fill the entire sky. So just to hit that point home, if you were to get in a spaceship and visit every star out to a distance of 30 light years, you'd visit just 10 sun-like stars. But in that same volume of space, you'd visit 250 M-dwarfs. And yet, despite their proximity and their prevalence, they aren't visible with human eyes alone. And the fact that we do need to use these powerful telescopes, these red-sensitive telescopes, means that they've been challenging to study observationally, and that there's, at this point, still quite a bit that we don't know about them. So I want to study these stars because I want to learn about the stars that are our nearest stellar neighbors. So, this would be like, this is the galactic sense of asking, who's our next door neighbor, who's the couple living down the street. And so learning about these stars is really learning about our place in the galaxy. But thinking a little bit more specifically, M-dwarfs are really excellent laboratories for stellar astrophysics. The star about which we know the most is the sun, and that anchors a lot of our explorations into stellar physics. M-dwarfs allow us to probe a regime that's very different from the sun. By studying these types of stars then, by studying M-dwarfs, we hope that we can answer questions like, how do stars produce their magnetic fields? How does magnetic energy heat the outer layers of stars? The other thing that makes M-dwarfs really exciting is that they're excellent targets around which to find and characterize exoplanets. So current estimates indicate that 60% of M-dwarfs have exoplanets. And in fact, the closest exoplanet to us is one that orbits an M-dwarf star. And I can say that for certain because the closest star to us is Proxima Centauri. Proxima Centauri is an M-dwarf, and we know that Proxima Centauri has a planet around it. In particular, it's a planet with a minimum mass of just 1.3 times the mass of Earth. So in sum, the kind of big overall picture or question that defines my research is, how do stars and planets change over time? What observations do we need to try to answer these questions? What does this tell us about how these objects, these stars and these planets, how do they work? How do they interact? So today I'm going to be sharing with you my recent work on spin and magnetism in M-dwarfs, and then some of our work trying to find and study exoplanets around young stars. So I'm going to start with some background on what an M-dwarf actually is. I'll then address the question of how do M-dwarfs spin down, and I'll briefly touch on the relationship between rotation rate and magnetism. And then lastly, I'll turn to thinking about how stars impact the planets that orbit them. I always like to start my talks with an introduction to M-dwarfs because I don't want to lose anyone on the first slide. So starting with the sun, we are going to think about the stars that are lower mass than the sun. And I know that these very low mass stars don't do a lot of really cool things like end their lives as supernovae, or since I talked with Alex G earlier today, you can't see them in dwarf galaxies nearby. They're just too faint. But I hope you'll come to appreciate them anyways over the course of this talk. So M-dwarfs span the range from about 0.6 solar masses down to the hydrogen burning limit at around 0.08 solar masses. So they span almost an order of magnitude in stellar mass. And to be fair, they are less spectacular than their higher mass companions. So a middling M-dwarf is about 1,000 times less luminous than the sun, and it will persist on the hydrogen burning main sequence for longer than the age of the universe. I separate M-dwarfs into different categories, defining these as the early, mid, and late type M-dwarfs, which is just indicating different mass ranges. So specifically, I tend to focus on mid to late type M-dwarfs, which are below about 1/3 of a solar mass. Mid M-dwarfs mark an important transition in stellar interior structure. So early M-dwarfs are partially convective and have an outer radiative zone like the sun, while mid and late type M-dwarfs are fully convective. So the M-dwarf spectral type actually includes this transition in stellar interior structure. And we'll see why this is important in a few minutes. There's a couple of things that, that I want you to know before we get started. And the first is the connection between stellar rotation and magnetic fields. So overall, faster rotating stars have stronger magnetic dynamos and stronger magnetic fields. A practical way to probe the magnetic field or the magnetic dynamo is by looking at magnetic activity. So magnetic fields heat the chromosphere and the corona of the star, and we observe this emission in these outer layers. And this gets called, just broadly speaking, magnetic activity. So the connection between rotation and magnetism is expected to depend on the interior structure of the star. In the standard picture of the solar magnetic dynamo, the interface between the convective and the radiative zones, that is the tachocline, is really important. So this is where the sun's magnetic field is strengthened and organized. So the sun's magnetic dynamo is often called the interface, an interface dynamo. In M-dwarfs, the boundary between the radiative-convective zones is deep in the interior, and the lowest mass M-dwarfs are actually fully convective, as I've illustrated in this totally accurate rendition of an M-dwarf on this slide. And so what this means in the context of the magnetic dynamo is that a dynamo where the tachocline plays an important role can't be responsible for the large-scale magnetic fields on M-dwarfs. So this means that the magnetic dynamo that we think powers the sun shouldn't operate in M-dwarfs. And as a consequence, we're going to expect that they'll show different relationships between rotation and magnetic activity and how these might change with time. Some of these differences are borne out in what we know about the evolution of angular momentum of rotation at young ages. So this plot shows rotation period plotted against age. And to illustrate the spin down process, I've taken some representative rotation periods for stars in young clusters. So these clusters have known ages, which allows us to trace out the rotational evolution of a given mass star. So here, the yellow dots are going to represent a kind of typical solar mass star. The red dots are going to represent a typical mid M-dwarf. So stars start out with a range of rotation periods and then experience some initial spin up as they contract onto the main sequence. M-dwarfs are smaller, they spin up to be faster. But you can already see that at these young ages of around, say, like 50 to 100 million years, the rotational evolution of sun-like stars at M-dwarfs is already diverging. So for sun-like stars, the spin down process is well underway. You can see we have here like a bifurcation. There's still some fast rotators, but most of the solar type stars have made it, have decreased their rotation period significantly. So that spin down process for sun-like stars is well underway by about 100 million years. And by 500 million years, the rotation periods of stars of a single mass and age have converged to a narrow sequence. And then they continue to spin down slowly with time. This is really the concept that underlies that technique of gyrochronology, using stellar rotation periods to determine ages. And then throughout this time, as the star is spinning down, the magnetic activity is declining. M dwarfs, on the other hand, take a longer time to reach their maximum spin rates. By 500 million years, which is roughly the age of the Hyades or Praesepe open clusters, mid to late M dwarfs have actually not yet begun their spin down process. And so trying to probe spin down in M dwarfs and what happens at these later times is very challenging because we don't have many M dwarfs with known ages, with known older ages. So these clusters that we use to trace out rotational evolution, the ones where the M dwarfs would be spinning down are just too far away at the moment to actually make progress and using stars and clusters. In the next bit of my talk, I'm going to address these two questions, trying to fill in the missing part of that diagram. So how do M dwarfs spin down? And what is the relationship between rotation and magnetic activity? Given the differences in internal structure between M dwarfs and solar type stars, we weren't sure really what we would expect. We thought that there would probably be some differences between what happened for sun-like stars and what happens for M dwarfs. Addressing these questions requires new measurements of rotation and magnetic activity, which is good because I'm an observational astronomer, and so I like taking data. And like I said, the mid to late M dwarfs in these nearby observationally accessible clusters have not yet begun to spin down. So the approach that I've taken is to look at M dwarfs in the field of the galaxy, where we don't necessarily know all that much about an individual star, but we can look at the ensemble and try to figure out what's happening. All right, so I'm going to start with stellar rotation, which is really kind of the bread and butter of my research. So the key behind measuring the way that I measure stellar rotation periods is star spots. So these spots modulate the brightness of the star as they rotate in and out of view. And the modulations are quasi-periodic. And so it allows us to determine the rotation period of the star. So we can do this with all sorts of data. A lot of times, the exact data that people who study exoplanets want is the exact same type of data that's great for studying brightness modulations. So a lot of really great stellar rotation work comes out of surveys that were originally designed to look for exoplanets. So this is an example of what some of this data looks like in real life. This is drawn from our work using data from the ground-based MEarth observatories, which is originally an exoplanet survey. So this is brightness versus time on one side, and then the phase folded light curve on the other side. So this M dwarf has a relatively long rotation period. So this is 83 days, so similar to, for example, Proxima Centauri. So you can actually just kind of see that this looks very similar to the PowerPoint illustration of rotational modulation that I showed before. So we've got these near sinusoidal variations, although you can see that the spot patterns are evolving with time. So we conducted a survey to measure rotation periods using data like this for nearby mid to late M dwarfs. I did not cherry pick this example as a particularly good looking case. So a lot of times the rotational modulation is really kind of blaringly obvious. It's actually kind of fun to like flip through all of these and see what they look like. So you can see part of that is driven by the fact that the amplitudes of variability are actually about 1% or 2% peak to peak. So these M dwarfs actually have fairly high amplitudes of variability.
Elisabeth, how much
Yeah.
differential rotation do M dwarfs have, and what latitude does this correspond to for when you say a given period, if there is differential rotation?
Yeah, so that's an excellent question. Generically speaking, I guess maybe a priori we would expect M dwarfs to rotate as solid bodies. So this rotation period would be for the star as a whole. But there have been some theoretical studies that do see some differential rotation in M dwarfs, but it's not. There's been no observational determinations of differential rotation. So I don't know what latitude this would correspond to. My best guess would be that that it's not going to make a huge difference whether we're observing spots near the poles or near the equator for what
I guess I'm
rotation
surprised that your first hypothesis would be solid body. Is that because of the strong magnetic fields? Because the sun is pretty highly differentially rotating with latitude, I thought.
Yeah, but the amount of differential rotation also depends on the on how the strongest differential rotation, if I recall correctly, is in the radiative zone. And then the differential rotation, I'm trying to remember what these plots look like. No one's actually ever asked me this question before, but I believe the differential rotation diminishes significantly when you get into the convective zone, and that shearing at that layer is actually part of the importance of the tachocline in strengthening the magnetic fields.
Thank you.
Cool. Yeah. So I'm going to show the rotation data on plots that look like this. So the y-axis is the rotation period, log scale. The x-axis is the stellar mass, also log scaled. I'm pretty much only showing M dwarfs here. So we get it kind of out to like really late K dwarfs on these plots. So these gray points are rotation periods that we compiled from the literature. And here in green and purple are the rotation period measurements that we made. So our survey was relatively unique in that it was sensitive to both very short periods. So like the fastest period we measure is about 1/10 of a day, and also to very long periods. So our survey spanned many months to years in some cases, allowing us to measure rotation periods that were months on month timescales. So the first thing to note here is that there are M dwarfs with very long rotation periods. So this, they get out to rotation periods of around 140 days compared to 25, 30 days for the sun, depending on latitude. And so the very first thing that is important takeaway here is that mid to late M dwarfs do spin down. So not all M dwarfs are rapidly rotating. And it can be particularly striking to look at this if I stop plotting the y-axis in log scale. And so this is the same plot, but with a linear y-axis. And you can see that mid to late M dwarfs have reached significantly longer rotation periods than even early M dwarfs do. So about 150 days is the longest period we've measured for a mid to late type M dwarf. 50 days is the longest period we measure for like a late K early M dwarf. So these low mass stars are spinning very, very slowly. So we then wanted to understand something about the spin down timescale. So how long does this process actually take? So since the stars in my sample are all of these random field M dwarfs, we don't have any unique constraints on their ages. So what the approach that we took instead was to constrain the age of a population of M dwarfs using galactic kinematics. So this plot shows total space velocity versus stellar rotation period. And so as stars age, their orbits through the galaxy are perturbed by gravitational interactions, and their space velocities would tend to increase. So if we look at a group of stars, the dispersion in the space velocity will tell us the age of that group in a statistical sense. So these are the data color-coded by stellar mass. And what you can see is that there is definitely a change in in the space velocities as a function of time. So our rapidly rotating stars have a narrowly constrained range of velocities. So that's indicative of a young stellar population. Our older sample, our longer period sample has a much wider range of space velocities, which is indicative of a much older sample. So when we were then placed some numbers on this, the error bars are relatively large, but what we were able to say is that the rapidly rotating branch is less than about 2 billion years old, and the slow branch has an average age of around 5 billion years, which is to say these are kind of average older thin disk stars. So all of these stars are in the solar neighborhood, so we do generally expect them to have ages less than about 8 to 10 billion years. So what we can say is that M dwarfs do spin down, and that happens by around a few billion years. So in contrast, as I illustrated before, a star like the sun only takes around 100 million years to leave this fast rotating branch and transition to a slow rotating branch. So while M dwarfs do spin down, they differ from higher mass stars in that they may remain rapidly rotating for a much longer time. And the gap you can see in between these two branches indicates that the transition from the fast to the slow group must be very rapid. So even though, yep.
I was just going to say, Andy McWilliam had a question. I just want to point out, he was asking if these are all thin disks, or what's this population from?
Yeah, so the sample of stars is M dwarfs within proper motion selected M dwarfs. This was pre-Gaia, within about 30 parsecs, and the majority of them are in the thin disk. There are some biases in the fact that it is originally a proper motion selected survey. So we actually did work to understand like what population of stars we were missing due to that kinematic selection. Did that answer the question?
Yeah, great, thank you. Cool. Keep going.
Okay, so now I wanted to kind of take a step back and place this in, go back to that original animation I showed you, showing the evolution of stars as a function of age, and place the field M dwarfs in the context of young clusters. So previously, I described how stars like the sun spin down with initially rapid rotation periods that then converge to a slow sequence. And with the advantage of data provided by both my work on the field and a number of different studies using, in particular, the K2 survey to look at M dwarfs in young clusters, we can look at the M dwarfs in the context of young cluster rotation. So this is the Pleiades, so it's an age of around 120 million years. And you can see that the fastest rotating stars in our field population correspond to the fastest stars in the Pleiades. Things look really different when we transition to one of these older clusters. So this is the Praesepe at about 625 million years. And there's been a substantial amount of evolution between 125 and 625 million years. So the most massive stars, the early M dwarfs, have converged to the slow sequence, like sun-like stars do. So you can see that off on the left-hand side of the plot, assuming this is oriented the same way. And then when we look at the kind of the early to mid M dwarfs, we can see that there's a dichotomy in the rotation period. There's some fast stars and some slow stars. And this is very similar to what we saw for solar-like stars at younger ages. Now, if we look at the mid to late type M dwarfs, as I already said, by the age of the Praesepe, they're all still rapidly rotating. And what you can see is that the rapidly rotating young cluster stars match up really nicely with the rapid rotators in the field M dwarf sample. And if we consider the slow sequence, you can imagine that we would end up matching the slowest early to M dwarf, the slow group of early to mid M dwarfs in the field if we just let this mass sequence evolve and spin down slowly with time. So what we would then expect is that we'll, as we move to field ages, we still have a persistent rapidly rotating, a rapid rotating branch, because it does take a pretty long time for this transition to the slow sequence to occur. But that we overall are getting an extension of the rotation mass relation all the way down into the M dwarfs, at least by ages of around 5 billion years. So the overall picture that we're seeing here in the field M dwarfs is kind of a natural consequence of the evolution that we trace out in single age populations with these young clusters. So now we've got this large sample of M dwarfs with rotation period measurements. And the next question we had was, how are rotation and magnetic activity related in M dwarfs? To probe magnetic activity, what I have done so far is to use H alpha, chromospheric emission. And that measurement, we're measuring the excess amount of H alpha emission for M dwarfs, since there is also a fair amount of photospheric emission at this wavelength as well, of course. So to give you some context of what we would expect, this is my PowerPoint version of the relationship between rotation, or between activity and rotation, based on what we see for sun-like stars, for example, in calcium H and K or in X-rays. So on the y-axis, we have some measure of the rotation, the relative activity level. Activity-induced emission compared to the bolometric luminosity of the star. On the x-axis, we have some number related to the rotation period. Many of us use empirically determined Rossby numbers. The important part is that the smaller numbers correspond to rapid rotators. The slower rotators are at the larger Rossby numbers. Both of these axes scalings mean that are intended to erase the impact of stellar mass. So as long as stars have the same underlying physics with regard to how rotation impacts activity level, they should all fall on the same line in this plot. So for sun-like stars, the rotation activity relation looks like this pink line with scatter, of course. So rapidly rotating stars maintain a saturated level of magnetic activity, while for slow rotators, activity decays with increasing rotation period, according to a power law. So this is what we see for more massive stars, for partially convective stars. We honestly did not expect to see the same thing for M dwarfs. Sorry about that. Let's see.
Looks good. You're back.
Cool, I'm back. Excellent. I actually don't have the regular indicators to tell me that I am back. Okay, so this is what we were kind of wondering if we would see. It's not what we were expecting, but if I actually show you the data, it is actually what we saw in the end. So there is a very clear relationship between rotation and magnetic activity for M dwarfs. And it looks a whole lot like it does for partially convective stars. And in fact, we have both partially convective M dwarfs and fully convective M dwarfs on this plot. And as far as we can tell, they don't do anything different from each other. So what does this mean? I'm honestly not quite sure. But what it is telling us is that however it is that rotation impacts the magnetic activity level, there doesn't appear to be a transition that corresponds to the fully convective boundary. So, one possibility is that it is in fact the same magnetic dynamo mechanism. Another possibility is that this is more related to how the heating occurs in the outer layers, and that the dynamos could be different, but that the observational result could be similar anyways.
I guess I'm surprised. Like, I guess it's smeared out, so maybe it's hard to tell, but if it was happening at a single Rossby number, convective Rossby number, the convective overturn time scale is going to, depend on the luminosity, and the luminosity can be quite a bit different. So I would have naively expected that the critical rotation period, when the Rossby number becomes the, say, order unity, is quite a bit different for these different, but I don't have a good sense of, quite a bit different. Is that, how
Yeah, no,
wide of a
you're
range is
absolutely
that
right.
on here?
I think so. My axes on here are, I probably should have changed them when I was giving this talk to the Carnegie audience versus the last colloquium I gave. The x-axis is actually Rossby number. And the y-axis is H alpha luminosity divided by the bolometric luminosity of the star. So all of the transition occurs at about 0.1, a Rossby number of about 0.1 in stars of all masses. The critical rotation period does change substantially as we go to the later type M dwarf. So it's about 70 days for the mid to late type M dwarfs. So like Proxima Centauri, for example, with a rotation period of about 83 days, is barely out of the unsaturated regime, even though it has such a long rotation period.
Okay, that's very interesting. Thank you.
So we see this decay in H alpha. It's also seen in many other tracers of magnetic activity. So this result is not alone. So these are two examples of that. So the plot on the left is in calcium H and K. This was data from Mike on Magellan and is work that's being led by my graduate student, Thomas Boudreau. On the right side, we're seeing the same thing in X-rays. All right, so to summarize, up until now, I've discussed how we use new measurements of rotation and magnetic activity to show that M dwarfs spin down, and as they do so, the magnetic activity diminishes. So it's similar to what we've seen for solar type stars, but the timescales are longer. So for the remainder of this talk, I'm going to switch my focus and talk about how star stuff impacts exoplanets, and then about our work to try to understand this from an observational perspective by finding and studying planets around young stars. So overall, stellar properties have a huge impact on exoplanets, from the fact that when we measure the radius of a planet, what we're really measuring is the relative size of the planet to the star. But when we think specifically about rotation and magnetic activity, there are two key impacts. First, there's an impact on the detectability of planets. So rotation and activity impact our ability to find planets via both transits and radial velocities. And then all of this high energy radiation can also impact the climate and habitability of the planets. Another potentially critical way a star impacts its planet is by shaping its evolution, in particular by driving photoevaporation of the planet's atmosphere. So this is an artist's rendition of this process in action. It's based on real data, and honestly, I think this is a pretty accurate picture. If you compare to the models that are in that paper, they do pretty much look like what's shown here. So this is Gliese 436b, which is a Neptune-sized planet around an M-dwarf star. And it's got this giant cloud of evaporating neutral hydrogen, which we can observe through a transit at Lyman alpha wavelengths. So this evaporation, Gliese 436 is actually not a young M-dwarf, but overall, we would expect this process to be stronger at young ages when we do have high levels of X-ray and UV radiation from the star. So since we know that rotation and activity decrease with age, one way we can try to understand the impact of photoevaporation is by looking at young exoplanets. So finding and characterizing planets that orbit young stars really more broadly enables us to study planet evolution. So we can explore the effects of planet evaporation by looking for signatures, either in the overall radius distribution of planets, or as in the case of Gliese 436b, by observing escape in individual planets and drawing conclusions about what the current escape rate is from those systems. We can also explore how planets' atmospheric compositions and chemistries are affected by obtaining the spectra of the atmospheres of young planets either with the Hubble Space Telescope or with the James Webb. This plot from Ben Toffelmeyer shows planet radius as a function of either mass of the host star or the insolation flux. So the gray points are planets of unknown ages, so they're drawn from the NASA database. But generally, they're field stars. They're usually in the thin disk. So that means they're going to be like a few to 10 billion years old. The colored points are planets where we do know the age, primarily due to membership in the Young Stellar Association. So the planets represented by the colored points are all less than 1 billion years old, with the yellow points being the older ones and the purple points being the younger ones. So we do know of a number of young planets, and especially if you look at the youngest ones, so the purple points, of which there are like 3, maybe 4 on the spot, depending on the color scaling of your monitor. They tend to be a little bit larger than the average planet. But there aren't that many young planets known, especially at the youngest of ages. And so we do need a larger sample in order to draw robust conclusions about this. So the Transiting Exoplanet Survey Satellite, which is to say TESS, has enabled us to expand the search to new places. And in particular, it's helping us not only to find new young exoplanets, but also young exoplanets that orbit stars that are actually bright enough that we can then try to follow these up to study their evaporating atmospheres, their atmospheric chemistries, maybe even try to measure their masses using radial velocities. So TESS launched in April that's actually almost 3 years ago now. And since I was a postdoc at MIT at the time and had my base in the TESS office, I was lucky enough to be able to make the trip to Florida to see it. So this is me at the launch, which was really a lot of fun, I have to say. So TESS's prime mission was only going to last 2 years, and it's already completed it. And this is an overview of this is TESS's view of the sky through its first 2 years. This particular image was made by my graduate student, Eileen Garcia Soto. She does great work on star spots, which hopefully I'll be able to highlight in a future colloquium. She made this back in October, and I really like it, so I haven't stopped using it, even though I'm really out of season at this point for Halloween jokes. So please forgive me for that one. So you can see that TESS surveyed about 70% of the sky. The cadence for most of the stars is about 30 minutes. And overall, and most stars were observed for a span of about 27 days. So many stars were also observed at faster cadence, so 2-minute data. And some also were observed for longer than 27 days. So as you start getting near the ecliptic poles, you start getting longer observational baselines. So the first step to studying young planets is to find them. So I'm the co-PI of a collaboration called TIME, which stands for the TESS Hunt for Young and Maturing Exoplanets. And our goal is to do exactly that. So find young planets around these nearby young stars with TESS so that we can ultimately study planet evolution. So the core team members I've shown on this slide, and I especially wanted to highlight Andrew Mann, who's the co-PI of this effort with me. But then I also wanted to highlight that a whole large number more people contributed than just this. So this is the 50-person long author list for my most recent paper. This is really like a worldwide collaboration with contributions from a lot of different people. And it makes it a lot more fun to do the projects, and I think also leads to significantly better science. So I just wanted to make sure that all these names got up here during this talk. And then also, I would be remiss if I didn't point out that especially during COVID, we've got a lot of other really important team members. Shown here is team member Charlie, who frequently helps with my research and my teaching. All right, so going back to Ben's plot from before TESS, we can add on the TESS-enabled discoveries. And you can see that this helps us probe new parameter space, especially at these much younger ages. So there's a lot more, basically there's more purple points on this plot than there were before. And these are the planets that members of TIME have led discoveries of. So in this talk, I'm going to highlight TOI 451b, C, and D. Since that's the project I've really been shepherding through this whole pandemic. But before moving on there, I wanted to basically kind of let you in on a secret, which is not a very well-kept secret. Exoplanet research is really often about stars. And Ben Toffelmeyer's recently accepted paper, I thought, highlights this particularly well. We initially identified the young planet as we thought it was in the Octans young group, but basically there's this whole venture. It turns out it's not in Octans, just happens to be nearby. But what we realized is that it is also a young star, and it has its own small family of co-moving stars. By studying this, this co-moving group, these neighbors, or we call them friends, we were able to place an age constraint on planet hosting star. So these are two plots from Ben's paper, lithium versus color and rotation period versus color. So the points in the background, so the blue is the Hyades, so blue is the oldest ones, red are the youngest. And the friends group, so the friends of this particular planet host are shown in red. And so we're able to use the lithium and the rotation periods to figure out what the age of this small association is, and therefore what the age of this planet host was. So similarly, the TOI 451 story begins with a stellar astrophysics story. So TOI 451 is a member of the Pisces-Eridanus stellar stream. That's a young stellar association that we just didn't even know existed until 2 years ago, despite the fact that it is practically in our backyard. So the stream spans a total of about 120 degrees, and you can see the locations of the stream members in this image here, as well as basically spread across the entire southern sky. So the Pisces-Eridanus stream was first identified by Meingast et al. Using data from Gaia. And then originally they actually thought it was about a giga-year old, and I hadn't taken much note of it at that point. But then using stellar rotation periods from TESS, Jason Curtis and his team used the relationship between stellar rotation and age to find out that the cluster is actually only 120 million years old. So this is really exciting because all of a sudden we have this rich nearby young association in which we can look for planets. And because TESS is nearly all sky, we already had the data in hand that we needed to look for planets. In fact, it was the TESS data that Jason used to determine the age of the cluster to begin with. And so I was really excited about this, in part just because of the synergy of these large public surveys and how it all kind of came together to provide this unique opportunity. This is the light curve for TOI 451 from TESS. This star has 2 TESS sectors, so it's a total of about 54 days instead of just 27. And probably the most striking part of this light curve, why I think it looks awesome, is the stellar variability. And this again, this is our star spots. This is a fairly typical rotation signal for a young star, for a young solar type star. But there are also signals of exoplanets in here. Each of the planet transits is indicated by one of the bars on the bottom of the plot. The initial alert from the MIT TESS team about this candidate planet actually only had 1 planet, but we quickly realized there are actually 2 signals there. You might be able to see, however, that there are actually 3 different colors of bars along the x-axis. So there are actually 3 different planets here. It took us about a full year to actually realize that there was a 3rd planet in there, despite some earlier signs that we missed. But in the end, it turned out to be we had a pretty lucky happenstance. So we'd collected Spitzer data to try to confirm the 2 planets that we knew about. And by the time we realized there was a 3rd planet, Spitzer's mission was over. We couldn't propose for new data. But it turned out that, as I'm showing in this plot, the third planet happened to transit at the same time as one of our existing Spitzer observations. So this is that overlapping transit. So TOI 451d, that's the largest outermost planet, is the big signal. And then the little dip at the trailing end of this is planet B. So that's the smallest and innermost one that eluded us for basically an entire year. In sum, we have 3 planets orbiting this young star. These are the phase-folded transits. We were able to validate each of these planets using some statistical arguments and a variety of ground-based data, as well as this data from Spitzer and data from Gaia. So overall, the system looks something like this schematic. So we have our solar mass host star. It's about 95% of the mass of the sun. And then there's 3 close orbiting exoplanets. The periods range from 2 days for the innermost to 16 days for the outermost. And the radii increase with increasing rotation period. So the innermost planet is 2 Earth radii, the outermost is 4 Earth radii. There's also a slight infrared excess in the archival WISE data that we used that indicates that there might be a dusty debris disk, a cool debris disk. And then there's also a co-moving distant companion that we think is itself a M-dwarf binary. So these 3 planets offer the opportunity for comparative studies of their atmospheres, and they are excellent targets for spectroscopy with the James Webb. So I'm going to wrap things up here. So we've completed our journey from stars to planets. We saw that M-dwarfs are the smallest and most common type of star, and that the difference in their interior structure differentiates them from more massive stars like the sun. Considering kind of the rotation and magnetic properties of M-dwarfs, we looked at a sample of nearby M-dwarf stars in the field of the galaxy. And we showed that M-dwarfs reach very long rotation periods, taking a few billion years to get there. And that there is a relationship between rotation and activity in M-dwarfs that looks very similar to the one seen for more massive stars. And then when we turned to exoplanets, I discussed how kind of these properties, these rotation and activity properties of the stars impact the evolution of planetary atmospheres. And I didn't tell you kind of the answers of how stellar activity impacts exoplanets, because we don't know the answer to that question yet. But I did share with you the recent discovery of a young multi-planet system called TOI 451 that we hope will help illuminate this question. So it's been my pleasure to be virtually here to share my work with you, and I'm happy to take any additional questions.
So that was great. Thank you, Elisabeth. If we have some time to take questions, I see hands are being raised. Lynn, you want to go ahead and ask a question?
Hi, Elisabeth. Thanks for the talk. I'm Lynn Hillenbrand from Caltech, kind of an interloper here, but enjoy attending the talk. I was wondering, with the rotation work, there's this interesting disconnect in the Gaia HR diagram for M-dwarfs, where there's this gap around the convective, fully convective region. Do you see any signs of something happening in rotations that would correspond to that with the large M-dwarf surveys now?
Yeah, so I only briefly investigated that, and I did not see anything. But at least with the data that I have, like that I showed you in this talk, I just think there aren't enough stars to actually be able to see that. So I think you need, we might have to wait till LSST to actually be able to answer that question, because I think like that signal in the HR diagram is relatively weak. And so I think we might need a similarly large sample of M-dwarfs with rotation periods. That's my guess, at least.
Thank you.
Andy, you want to ask your question?
Hi, yeah. So you talked about investigating using kinematics to study the ages of these systems and the slowdown with age. But I know there's been some work on widely separated binaries where one member is an M dwarf and another, more massive star, and there presumably you could use gyrochronology to get better ages for the M dwarf. And if they're widely separated also, then maybe there wouldn't be some tidal effects on the rotation. I wonder if there's been any work on that and whether it's consistent with what you're finding from the kinematics.
I'm not familiar with any published work, but there's certainly some ongoing efforts in that respect. There's the Hawaii group is actually using M dwarf, white dwarf binaries to try to answer that question. I think part of the problem is that, actually Alex and I discussed this earlier, the binary rate goes down for M dwarfs. So M dwarfs are actually more likely to be single than they are in a binary system, which gives you a smaller sample to work with. And then there's the challenge of actually being able to detect the period in the M dwarf star itself. We have a very high success rate in the survey that we did, but it's not necessarily feasible to target every individual star with the amount of observations that we did for our survey. I personally have some interest in exploring this question using data from tests. I think that is a really good hunting ground for that question. But yeah, I think overall that I hope that they paint a similar picture, but I'm not aware of any published results that actually show that.
Okay, thank you.
Any additional questions? Alex.
Hi, Elisabeth. My question is maybe a little silly, but I'm wondering if you found 3 planets around this M dwarf, but it has a companion, is it surprising that we didn't find planets around the companion?
Oh yeah, so the host for TY451 is actually a sun-like star.
Oh.
And then the M dwarfs are actually like 5,000 AU away. Okay. But I think there is a very interesting question there of how does being in a binary star impact the detectability of planets, which there certainly seems to be some effect from that. I'm not an expert in that area, but there is an effect there. I think if you found planets around one star in a binary, I think a priori you wouldn't necessarily say that you would expect something particular from the other one, unless they were aligned. If you would expect alignment between the stellar spins in the binary, then if the planets are also orbiting in that same plane, then you might have a bias in terms of detecting planets around both stars in a binary pair. And there are some indications of that. So DS Tuck AB is another young planet that we studied. And what we see is that it seems most likely that, let's see if I can say this all, the rotation axis of star A, the rotation axis of star B, and the orbital axis of the planets around star A are all fairly well aligned.
Okay, cool, thank you.
So one last question I had, I was curious about this debris disk around the star. Could you just maybe discuss further how common it is to see debris disks in planetary systems? And is this another interesting constraint on the age to have this debris disk still existing?
Yeah, so we don't know much about the debris disk. We just have a WISE far infrared excess at like 12 and 22 microns, which basically tells us that it's cold. In terms of the presence of disks, or specifically of disks that would have infrared excesses at those wavelengths, so that the prevalence of disks does decline with time. It is totally reasonable to have a disk around this kind of disk around a sun-like star at 120 million years. I think, yeah, I guess that would provide some additional confirmation of it being a young system. We didn't really take that into account when considering the age of this star.
Great, thank you. There's more slots available if other people would like to sign up to talk with Elisabeth later today. But otherwise, let's thank Elisabeth again for a nice talk. So thank you. I'm sorry I could be the one person to applaud, but yeah, thanks a lot for visiting your virtual visit. You know, I guess I'll talk with you later.
Yeah, thanks for having me. It was my pleasure.